Hello, good morning. Hello, are you with me? Can you hear me, guys? Yes, okay, good. All right, good morning. I think we still have 1 minute. Just to remind you, please do not touch the recording. I did recording by two ways, one using the team, the other one using my own software. So you will, inshallah, you will definitely get a copy of the recorded session. Okay. Since the lecture is supposed to start at 9, I have only 1 minute now. Let me just ask this. Anybody has any question on the previous lecture before we start? Anyone has any question? Yes? No? Okay. Hello?
I have a question regarding the chapter number 2.
Chapter 2. Okay. Who's with me? Hello?
It's Bilal.
Bilal. Tell me, Bilal.
In problem 2.34,
Yeah.
we multiplied mass with the work shaft.
Okay.
So I was confused with this, how we can multiply the mass with work shaft
Well,
in order to get the unit?
Yeah, well, let me tell you, whenever you have the mass, then the final answer is supposed to be as extensive property. In other words, if it is in joule per mole, you have to multiply it by mole, or if it is in joule per kilogram, you have to multiply it by kilogram. Now, in 234, it was English system. So it was in BTU per pound mass. Then you have to multiply by pound mass so that you can get it as extensive property. So it's only a matter of units here. You get the idea, Bilal? It's
Doctor.
Yeah, it's only because of the units. That's it. Make sure that all terms are consistent. In other words, you can solve the whole problems as in BTU per pound mass, but the final answer, you have to multiply it by the mass or mass flow rate. Depends on the question. If it is a flow system, normally it is mass flow rate, not mass. Yeah, Bilal?
Okay, thank you, Doctor.
Okay, you're welcome. Anyone has any other question? Okay, so officially I can start the lecture today. Don't worry, if you still have a question, you can raise the question today in the afternoon session at 1 o'clock because we have a tutorial session. All right? Okay, so what do we have for today? Just a brief recap on what we did last lecture. Last lecture, we focused on ideal gas behavior and how can we deal with the first law of thermodynamics for ideal gas. And I already covered this slide, but just to remind you with it, we applied the first law of thermodynamics and we said, what if it is ideal gas? Then because we had replaced W with minus PDV here above, then we found that it has three variables: pressure, volume, and temperature. So two of them are independent. So that's why we reduced the number of variables in the equation. And then in this case, we had two variables per equation. Okay, so that's basically what we did last lecture. Then we said, okay, now for ideal gas, we have several processes. Yesterday, well, not yesterday, it was Sunday, we started with isothermal process. And we mentioned that if temperature is constant, then delta U is 0, delta H is 0, and we derived the equations for Q and W. If it is isobaric, means that the pressure is constant, and we also derive the related formula for it. I think here where we reached, am I right? Well, I also covered isochoric, if I'm not mistaken, and if with isochoric we said there's no change in volume, and that's why the work is going to be equal to 0. This is the main important feature with isochoric, and because W is equal to 0, then the first law of thermodynamics will not have W, you can see there, so that's why Q is equal to delta U. And the main difference here in ideal gas compared to the general equation that we explained before, that here delta U, it is still integration of CV dt, but CV is only function of temperature. Same thing with the CP here. CP is only function of temperature. Okay, that what we covered last time. Okay, so to start with today, it's adiabatic process. Now, what I will do, adiabatic process simply means we have no heat transfer. This is what we mean by adiabatic. But I want to add one thing here. Adiabatic means Q is equal to 0. But all equations that will be derived today are based on considering heat capacity as constant. That is additional thing we are going to consider in today's lecture, that heat capacity is constant. You will notice later on that we won't be able to integrate easily if the heat capacity is not constant. So this is additional thing that we will add today. Okay, now back to the 3 equations that I derived last lecture. I'll go back to the equation just to remind you. Now here, last lecture, we said that we have 3 equations at which I made the equations function of 2 variables only. Here function of TV only, here is function of TP only, here is function of PV only, pressure and volume only. So if I said it's adiabatic, means what? Means dq here is 0. Am I right? In the 3 equations. Now what? Okay. Okay, what does this mean? When I say dq is equal to 0, means the 3 equations, look at that. What I did here, I just support the 3 equations that we derived before. Forget about what's written here in green and pink. Just let's focus on the blue equation here. Okay, that was the first equation derived there, that is function of T and V only. Previously, it was dq here on the left side. Now I put dq is equal to 0 because I have adiabatic process. Okay, so what I will do the same for the 3 equations. This is the first equation, that is function of T and V only. This is the second equation, that's function of T and P only. And that is the third equation, that's function of V and P only. All of them, I made dq is equal to 0 because it's adiabatic process. And why this is useful? Okay, I'll go back to each equation individually. Why this is useful? Look at it. Now, if I have to 0, then I can rearrange the equation. I'll just rearrange it for you just to see what's happening here. I have CV dt is equal to minus RT dV over V. All right? So if I rearrange it, I have T on the right side, but I have dt on the left side. So what I will do, I will just bring the T to the other side, while the CV, I will take it to the right side. So this is how I will do it. So it's dt over T is equal to minus R over CV dV over V. Okay, now if I will integrate, considering here the integration from T1 to T2, and here I will integrate considering the integration from V1 to V2 because I have dV here. Now R over CV by its own is constant. Now, is CV always constant? No. For ideal gas, CV is a function of temperature only. But you can see here in the title, I will run my lecture today considering constant heat capacity. So that's why all that term can be taken out of integration. So if this is the case, the integration of dt over t is going to be ln T2 over T1 here minus RCV outside the integration, and then the integration of dV over V is V2 over V1. Sorry, ln V2 over V1. Okay, I will just repeat here what I have for those who did not follow with me. What I have here, I have this term, the integration of dt over t, the integration of it is ln. Then I have here integration minus R over CV. That I have taken it out of the integration, so I have dV over V inside the integration. So when I integrate that, it's going to be ln V2 over V1. Is that clear so far? Yes? I want to see at least one yes. Excuse me. Yes? Hello? Yeah, great. Okay, so what we have here then, I have ln here and I have ln there. Now, you remember from math, Okay, you remember from math, we tend to say if you have ln x to power n is equal to n ln x. That's a rule you have taken it in math. So because of that, what I will do here is this. I'm going to take that r over cv back as a power here. In other words, I have ln t2 over t1 equal to ln v2 over v1, but the power here minus r over cv. Okay? Now, again in math, let me just put a line here. Again in math, we also studied that if you have ln in both sides, you can cancel the ln in both sides. This will give us a very famous equation. What is that equation? T2 over T1 equal to V2 over V1 all to power minus R over CV. Now, if you check this equation, if you compare this equation, the one I just derived for you, and the equation written here in pink, it is same, except that instead of having minus R over CV as a power, I have R over CV as a power. And here it was minus, there in the pink equation it was positive. Why is this? Because I have here V2 over V1 in my derivation, while in the pink equation it was V1 over V2. In other words, they are same. So what I did now, I just derived for you the pink equation, that there is a relationship between temperature and adiabatic process. Okay, then before proceeding, why this is useful? الحين, previously, when it was isothermal, we said T1 is equal to T2. Wonderful. When it was isobaric, we said P1 is equal to P2. Excellent. When it was isochoric, we said V1 is equal to V1 is equal to V2. Fabulous. But here, when it is adiabatic, what is the relationship between pressure, volume, and temperature? We don't know. And this is exactly what I'm doing now. I'm trying to give you equations that relate temperature and volume, temperature and pressure, pressure and volume. I hope this is clear for you. Yes? I want to see yes, please. If no, tell me no, and I will repeat. No voice? If no voice, you can write. Okay, great. I can see so many yeses. Wonderful. So the first step I did here is simply that I showed you a relationship between temperature and volume. From where? From this blue equation. If I repeated the same thing, let me clear the board so it becomes things neat. Okay, if I repeated the same thing for the other equation, which is the second equation we derived last lecture, we will rearrange it exactly same approach, which I did. I will not repeat it. You can practice it yourself. If you rearrange it the same way I did before, you will end up with this equation, which is T2 over T1 equal to P2 over P1 all to power R over Cp. What does this mean? It means I have now another relationship, but not between temperature and volume. It is between temperature and pressure. And that I can use it only with adiabatic process, as you can see there in the title. And then repeating the same thing with the third equation. If I rearrange this equation, I will get Cp P1 P2 over P1 equal to V1 over V2 all to power Cp over Cv. Okay, those three pink equations are very, very, very important equations for today's lecture. Okay, I need to add one thing. In thermodynamic textbooks, they did this arrangement, and I'm going to show it to you here. I'll start with this equation. This equation means what? Means P2 over P1 equal to V1 over V2, but each one of them has a power of Cp over Cv, like this. Okay? All right? So what does this mean? It means that if I did cross multiplication for the both sides, I would have P2 V2 equal to P1 V1, but each volume has a power of Cp over Cv. Okay? So to simplify it, we have a term in thermo called gamma. And gamma is defined as the ratio between Cp and Cv. Okay? That gamma is called specific heat. Cp is a specific heat capacity at constant pressure. Cv is a specific heat capacity at constant volume. Gamma is the ratio between the specific heat capacities, both of them. Yeah? And for your information, gamma is always greater than 1 for ideal gas. Reason? because Cp is always higher than Cv. Keep in mind that Cp is equal to Cv plus R. In other words, Cp is always greater than Cv. So that's why for ideal gas, gamma is always greater than 1. Okay, so in other words, as a conclusion, I can just write here this. If P2V2 to power gamma, now if I just rewrite this equation, I can just rewrite it as, okay, let me see if I have a space. I can rewrite it as P2 V2 to power gamma equal to P1 V1 to power gamma. What does it mean? It means any PV to power gamma equal to constant. Okay, and that is another form of writing this last pink equation. And then, question here, can I do the same for the first two pink equations? Yes, I can do the same. What does it mean? Since I know that gamma is equal to Cp over Cv, I can just rewrite it in a different way. Look at that. Here, they give me R over Cv. So the question here, can I write R over Cv in terms of gamma? Of course I can. What is R, guys? R is the difference between Cp and Cv. So I can just say like this. R over Cv is equal to Cp minus Cv over Cv. Correct? So in other words, it is Cp over Cv minus 1. Doctora, how did you do this? Because I have 1 in denominator. So I divided the numerator Cp over Cv minus Cv over Cv is 1. Okay? And I think you all know that Cp over Cv is what? Is gamma, according to the definition of gamma. So this means that this is equal to gamma minus 1. Okay? All right? So if that is equal to gamma minus 1, let me just use another color so that things doesn't become a mess. If that is equal to gamma minus 1, now I have this as a gamma minus 1. All right? So I can then write T2 over T1 equal to V2 over V1. Doctora, why you did this? No, I would keep it V1 over V2. I don't want to confuse you. V1 over V2 all to power gamma minus 1. Which means if I did the cross multiplication of both sides, I will have T2V2 to power gamma minus 1 equal to T1V1 to power gamma minus 1. What does this mean? This means that this brings another important equation that say T to power gamma is constant value. You understand? So, Doctora, again, what you want to say? I want to say that you can either use the pink equations or the equation that I put in boxes here. Both are equivalent, but when I am going to use the pink one and when I am going to use the ones in the boxes, the answer is, if in the question they only give you gamma, then you cannot apply the pink equations because pink equations consist of Cp and Cv. If in the question they give you only gamma, then the only option is that you use the one in boxes. But I can repeat the same thing with the equation in the middle here. Okay, that I will leave it for you to try. Same concept. You replace R over Cp with its equivalent gamma. Again, how? You will remove R and put Cp minus Cv, like what I did here, and then you will find its equivalent value in terms of gamma. So to show you this in detail here, or in summary, here is the equations. So what do we have? We mentioned, I'll go back to this slide here. I will just clarify. We put temperature and volume relationship here. We put temperature and pressure relationship here. We put pressure and volume relationships here. And to make it in terms of gamma, those are the equivalent representation. Tv to power gamma minus 1 is constant. Tp to power 1 minus gamma over gamma is constant. Pv to power gamma is constant. So those are the three equations in terms of gamma. And gamma is called specific heat ratio because it's the ratio between the specific heats, and it's defined as Cp over Cv. Okay, in conclusion, when can we use those equations? Okay, we can use them if I have ideal gas, constant heat capacity. Why constant heat capacity? Because if the heat capacity was not constant, I was unable to take it out of integration, if you remember when I did the derivations. And it's supposed to be mechanically reversible, adiabatic process. Adiabatic means adiabatic expansion or compression. Now, there's something here called isentropic. I will explain that in detail next chapter. But I want you to know that whenever you have reversible and adiabatic together, we call it isentropic. So I will just write it here to clarify it. The word isentropic, it means it is adiabatic and reversible. So adiabatic and reversible, when you add them together, it's going to be asentropic. This is a thermodynamic concept. Why? I will explain it next chapter. But you have to know that whenever reversible and adiabatic comes together, we call it isentropic. Okay. Now, can I use this for real gas? It says here that if you use it for real gas, it gives satisfactory approximations, but you will get deviations. So we can use it, but it gives satisfactory approximations according to what Smith mentioned. Okay, so what we have done so far. Last lecture, we explained isothermal, isobaric, isochoric process. Today, I explained, now I explained the adiabatic. Now, if you remember the pattern of our procedures last lecture, for the isothermal, we said T1 is equal to T2, and then we found Q, W, delta U, delta H. For the isobaric, we said P1 is equal to P2, and then we found Q, W, delta U, delta H. We repeated the same thing for the isochoric. We said V1 is equal to V2, and then we defined Q, W, delta U, delta H. We have to do the same here. We said it is adiabatic, and what we did so far, we only found relationship between temperature and volume, pressure and volume, temperature and pressure. The next question now is what? What is Q? What is W? What is delta U? What is delta H? This is the answer that I need to, or this is the question that I need to answer now. Okay. For adiabatic process, of course, Q is equal to 0. So originally, here I had dQ, and now my dQ became equal to 0, correct? So in other words, if I have adiabatic process, then dW is equal to du, and you know that du is equal to CV dt. This is the differentiation form, right? Okay. If you have constant CV, then CV can be taken out of integration, and the dW, if I integrated it, it's going to be W. Integration of du is delta U, and the integration of C dt is CV delta T, provided that CV is constant. Okay? All right. That's wonderful so far. What I will do now, things are clear. We know how to calculate W. We know how to calculate delta U. Now we will talk about Q is 0. Now what's remaining is only delta H. But let me play with the equation a bit. And then, why we want to play with the equation? Because sometimes in the question, they give me the value of gamma. So I need to know how the equation can be rewritten if gamma was given. Now gamma is Cp over Cv. What I did, I replaced Cp with Cv plus R. You can see there, right? Let me use the highlight so you follow with me, the laser pointer. So the Cp itself is equal to Cv plus R. Now you can see here from this relationship that Cv over Cv here is 1, and what's remaining is R over Cv. Now can we rearrange this equation? Yes, we can. Now it says here, I need a pen now. Okay, what it says here, it says that gamma is equal to 1 plus R over Cv. Now, can we rearrange it somehow? Yes. What I will do is this. I will take gamma, I will take 1 to the other side. Gamma is equal to 1 plus R over Cv. I will take 1 the other side, so it's going to be gamma minus 1 equal to R over Cv. If I want Cv in one side, then Cv is equal to R over gamma minus 1. Can you see that? Okay, so what I did here, simply, I just rearranged it. And this gives me an expression for Cv. And the doctor, why you did this? Why is that? Because I want to put this Cv. Okay, so in this case, delta U is going to be, it can be written as, instead of Cv, I can put R, that is, look at this, R over gamma minus 1 instead of Cv. Okay, when this is useful, especially when Cv was not given, but gamma was given instead. Is that clear? Clear so far? Any question? Okay, you can either use the mic or write for me in the conversation, in the chatting. Clear? Clear?
Yes.
Okay, great. All right, so this is how to find W if the gamma was given. And then more complication, well, not more complication, but more elaboration or playing with the equation just in case some information were not given in the question. الحين, what I did so far here, it was R delta T over gamma minus 1. In other words, if I can just rewrite it here, it's RT2 minus RT1 over gamma minus 1. Now, from ideal gas behavior, you all know that each RT term is actually PV term because PV equal to RT. يعني I can simply replace each RT with PV. That is another way of writing it. Now, when will I be able to use this equation? If pressure and volumes are given in the question rather than temperatures. Okay, so as a conclusion, now we have several forms of W. It can be written as R delta T over gamma minus 1, or delta PV over gamma minus 1, or delta U because W is equal to delta U, which is equal to CV delta T. When these forms are applicable, we use them for adiabatic, compression or expansion process, closed system, mechanically reversible or not. Wow, that is strange here. What we did when we started the derivation, we started considering W is equal to minus BdV, and we said it's supposed to be mechanically reversible process. But now Smith changed his mind. Once he reached until the end, he wrote in a bracket here, reversible or not reversible. What does this mean? It's simply because, anybody can guess why here he changed his mind? He just put reversible or irreversible. Maybe tricky. I know it's tricky because we did not explain that before. Anybody want to try? Think of a reason why this equation, the W equation here, it doesn't matter whether it's reversible or not reversible. Anyone want to say something?
It's just because the work is PV, the effective pressure and volume.
Okay, and this means what? Yeah, Ali. Okay. Yeah. Tell me. Yeah, you're just about. Okay, can I just give you hints? Look at W here. Look at W here. It is function of temperature over there, right? R is constant and it's only function of T1 and T2, correct? Here it's only function of
Yes.
P1, V1, P2, and V2. What does it mean? It simply means that it's only function of properties. It's not function, it doesn't depend on the path, no more. When we derive it now, you can see, as long as I know T1 and T2, or as long as I know P1, V1, P2, V2, then I can find W. This means what? This means it doesn't depend on the path in this equation. In other words, whether it is reversible or irreversible, I don't care, as long as the initial and final condition hasn't changed. You get the idea? Yeah, it means whenever you made the derivation and you found that the derivation was based on properties only, then you can use the same thing for reversible as well as for irreversible. انزين الحين here I found W, and we know that W is equal to delta U. Now W, delta U, Q are known. How about delta H? How about delta H? How can I find delta H if it is adiabatic process? Does it matter? Does it matter? Yeah.
The first law.
Okay, well, actually, you have more than one option. One is using the main equation. So Cp is constant delta T. Now, the point is, if you applied first law, there is no delta H in the first law for a closed system. For a closed system, you have delta U there. So delta H cannot be found from the first law. But you can find it either from this relationship, or you can just find it from delta H equal to delta U plus delta PV. And remember, we already mentioned before that this equation is universal and can be applicable for any process, including the adiabatic. And delta PV can be replaced by delta RT as well, because P is equal to RT with ideal gas behavior. Okay, guys? Clear so far?
Which, Doctor?
Say it again, Ali.
Which one is more accurate? Like, which one do we use without having to assume some conditions? Like, in which case do we choose the first equation when do we choose the second?
No. Both of them, for ideal gas, both of them are applicable. You can use delta H is equal to integration. You will get the same answer. But what I'm saying, with the first equation, if Cp is constant, you can take it out of integration. With the second equation, with delta PV, if PV values were not given, you can replace it with RT values. But both of them will give the same answer if you are dealing with ideal gas behavior. Any question? Yeah, actually, Ali, to make it even more clear, the second equation is used for any process, including ideal gas, of course. The first equation is used for any process, but if it is ideal gas, then Cp is function of temperature only. Wonderful if it is constant, so that I can take it out of integration. Okay? Okay. Any other question, guys? Okay. Now, something you have to know from industry. In industry, usually the final temperature and final volume are not given. And because of this issue, we try always to eliminate them. Eliminate them means what? Remove them from the equations because they are normally unknown. So what I will do here, I will just show you how to play with the equation furthermore. Wow, that looks complicated, right? Okay, let me clarify. The last equation we reached to here is R delta T over gamma minus 1 is equal to W. Let me just write it for you here. W is equal to R delta T over gamma minus 1. So if I wrote it, I'll just write it in a different way. RT2 minus RT1 over gamma minus 1. Or I can write it as P2V2 minus P1V1 over gamma minus 1. Zin. Doctor, where you bought those from? From the previous slide. Those are expression for W. Now, if in the question or if in the practical problem, V2 and V2 are not given, then I cannot apply this equation and I cannot apply this equation because T2 is there. I cannot calculate the work. So how can I eliminate them? And this is the point. Here we gave you an expression. And to explain how we got that expression, I will derive it for you right now. So let me start with this. Okay. W is equal to RT2 minus T1 over gamma minus 1, which is what? Which is the first equation here. Now let's take T2 as a common factor. So if I take T2 as a common factor, then I would have RT2, and inside the bracket, I would have, I will take T1 as a common factor. Easier, I think. RT1, and then I will have T2 over T1 minus 1 divided by gamma minus 1. Okay? If you remembered in the relationship of adiabatic process, there is an equation says T2 over T1 is equal to P2 over P1 all to power R over Cp. Okay? That equation is really important because I can replace T2 over T1 by P2 over P1. So in this case, the T2 that I want to eliminate can be done here because T2 can be replaced by P2 over P1. So in this case, I would have RT1 into P2 over P2 over P1 all to power R over Cp. And in the previous slides, I already prove or you can prove that R over Cp is equal to gamma minus 1. Well, I can prove it for you if you want. Let me prove it for you so things becomes easier. Okay, R over Cp means what? Means Cp minus Cv over R. I just replace R with Cp minus Cv. Okay, Cp minus Cv, and here I put Cv as denominator. So Cp over Cp is 1 minus Cv over Cp. So if you rearrange it, here it's going to be Cp, if I just rearrange it or re-express it by gamma, so it's going to be 1 over, here I have Cv over Cp. Cv over Cv is what? Is 1 over gamma. So in this case, cross multiplication for the denominator and numerator. So I will have gamma minus 1 over gamma. So in this case, here I can replace it with gamma minus 1 over gamma minus 1. Divide it by gamma minus 1. Okay? Clear so far? Any question? I know with the math sometimes students get lost. Clear?
Yes.
Okay, wonderful. So other than Ali, I just want I don't want to feel guilty. Others, can I see just yeses in the post? I need to see yes. Okay, thank you very much. I can see so many. Wow, that's wonderful. So in this case, I have RT1. Well, this is by its own is an excellent equation because I don't have T2 anymore. I don't have V2 anymore. I can use it. Wonderful. To calculate what? To calculate W. But what if instead of T1 in the question, they give you P1 and V1? Well, still fine. I can remove RT1 and put P1, V1, let's P1, V1, and then I can just put the remainings as they are, which is gamma minus 1 over gamma minus 1 divided by gamma minus 1. And then, you don't have to memorize all those equations. You can derive them if you want, but I will have tutorial session this afternoon. We will solve problems and you will see that you can just easily link between equations when you practice. Okay, so that just defines how to play with the equation to eliminate T2 and V2. All right, so if this is the case, I will just clear everything and show you this final equation. This is the one I just derived for you. And then if I replace RT with PV, I'll the other equation. خلاص شباب؟ انزين. With the Q, well, with this equation W, you just have to know, I will repeat, that equation is used for ideal gas, constant heat capacity, adiabatic process, mechanically reversible closed system. Right? If you used it for real gas, then you would get satisfactory approximation as we mentioned. Okay, any question?
Can
yes.
we use this for the irreversible?
That's wonderful. Now, based on the derivation, if for example, in the question, they give you initial condition and final condition, then this W is W for the process regardless of reversible or irreversible. But you will notice from now onwards when we start solving, according to the derivation, it can be used for both. But I will show you in the equation while solving how to be in the safe side. To be in the safe side, you would need to calculate W for reversible, and I will teach you through the efficiency how to calculate W for irreversible. Don't worry, Ali, and the rest of you have the same question. We will come to that while we solve problem. But yes, if it's only functional properties and through the derivation, we only depended on initial and final condition, then yes, it can be used for reversible as well as for irreversible. Okay, the question here. And then, Doctora, in the question, if they give me the value of gamma, can I apply the equations? Of course you can. And then, what if I will give you rule of thumbs here? There are rules. Gamma is equal to 1.67 as a rule of thumb, as an approximated values, if you have monoatomic gases. And then, Doctora, what does it mean, monoatomic gases? The gases with only one atom. Like, for example, here, helium or argon. It's only one atom. If you have diatomic gas, diatomic means two atoms, whether they are same atoms or different. O2 is diatomic gas, but CO is also diatomic gas. It is two atoms, but two different atoms, or it can be two atoms, but same. So diatomic gases mean the gases with two atoms. So gamma is equal to 1.4. All right? Or gamma is equal 1.3 if you have polyatomic. شنو يعني polyatomic? Polyatomic means more than two atoms. Like, yeah, more than. Polyatomic means more than two. Okay? In other words, here you have CO2, it consists of three atoms. خلاص? إنزين. Doctora, can I use those gamma values while I solve? If they have been given to you in the questions. If I did not give you those values in the question, then you have to use the information given in the question. But as a rule of thumb in your life, in case you want to solve the problem and you don't have the gamma values, those are just a rule of thumbs. It means guidance on the values of gamma that you can choose. And then I have a question here for you. How, Dictora, you said gamma is a constant value while Cp is a function of temperature and Cv is a function of temperature. يعني gamma is equal to Cp over Cv. True? And then Cp is function of temperature and Cv is function of temperature. So how come gamma is not a function of temperature? How come gamma is a constant value? صح ولا لا?
صح.
Yeah. The answer for this. Anybody would like to answer? Maybe you can guess.
The constant cancels out يعني.
Sorry?
أنا بوقع constant فما يفرق يعني.
They are, well, actually, they are not constant. Ali, they are not constant. Here, I'm just saying Cp is constant of temperature, Cv is constant of temperature. But when I give you the value of gamma was constant. And then the answer is gamma is less sensitive to temperature than Cp and Cv themselves. يعني while Cp is changing with temperature, Cv is changing with temperature, the change in temperature is almost same such that gamma would be independent or less sensitive to temperature change. You understand? يعني as a ratio, that effect of temperature change is just negligible. خلاص? Clear? Or you need further clarifications? Clear. Okay. Last thing we want to say in today's lecture, and the afternoon session will be just solving problems. Okay, we covered isothermal, isobaric, isochoric, and adiabatic processes. Last process here, it's called polytropic process. And whenever I explain this topic, I said this statement. If I were given the chance to rewrite this book, I will put polytropic, the first one. Why? Because it is the mother of all processes. يعني isothermal is one type of polytropic. Isobaric is one type of polytropic. Isochoric is one type of polytropic. Adiabatic is one type of polytropic. In other words, polytropic means turning many ways. It can be any way we can take it. So that's why polytropic covers all the previous ones, plus any ones that is none of those. Okay? So for that reason, we put an expression for it, that PV to power, look at that, PV to power delta is constant. This is called delta. And here PV to power delta is constant. And then, Doctora, what does this mean? It means simply it depends on the value of delta. The path really depends on the value of delta. To make this one clear, what I did here, I put PV to power delta equal to constant, TV to power delta minus 1 is equal to constant, TP to power delta minus 1 over delta equal to constant. Wow, that reminds us with which process? Which process? Anybody remember? Can you write for me in the chat or using the mic? Having those. Adiabatic, exactly. Thank you very much, Muhammad. Thank you. Who else? Okay. Yeah, the adiabatic, Abdurrahman, that's true. So, yes, it reminds us with the adiabatic, but instead of putting gamma, we put delta here. And then, what does it mean, Doctora? I will show you. I will skip this for a minute, huh? I will show you. This is a very wonderful plot. When I say, look at that, huh? When I say, according to the relationship, this is PV plot, right? يعني this equation, PV to power delta is constant, is valid there. So what I will do here, look at this with me, huh? Very careful, huh? PV to power delta is equal to constant. الحين mathematically, if my delta is equal to 0, what does it mean? Means PV to power 0 equal to constant. True? It means anything to power 0 is 1. It means P is equal to constant. So, which means that if you have, sorry. Okay. If you have delta is equal to 0, means I have isobaric process. So can you see why isobaric process. نعم.
Isochronic لا ولا isobaric.
Isobaric. Constant pressure means isobaric. Why isobaric? Because I put delta equal to 0, يعني v to power 0. V is not constant, علي. But any value to power 0 is 1. Huh? 2 to power 0 is 1. 10 to power 0 is 1. Correct? So that's why I remove the v. V is not constant here. P, according to the final conclusion, P becomes constant. So if delta is equal to 0, then it is isobaric process. And isobaric process is represented by horizontal line. So isobaric is one type of the polytropic if delta is 0. خلاص؟ إنزين. Let me just choose another value for delta. If delta now is not 0, my delta is 1. What does it mean, guys? Let's substitute. PV to power 1 equal to constant. What does it mean? Means PV is constant. الحين if PV is constant and its ideal gas means what? PV is equal to RT, صحيح? If PV is constant means RT is constant. يعني T is constant. Means I have what? I have isothermal process in this case. So when my delta is equal to 1, then what? Then it is isothermal process. And the isothermal process is represented by this curve. Inzeen, can I show you proof? Very interesting proof. If you remember the PV diagram we explained beginning of this chapter, that the pressure volume relationship, if you remember, it was like this. خلاص? And here we are dealing with ideal gas, يعني the gas phase, this region. So each line here, it is isotherm, يعني T is constant. So can you see why this looks like that? It is simply because it is this region. This is the curvature. This is isothermal. خلاص شباب؟ معي?
Yes.
Okay, good. Now, and we already said that if my delta is equal to gamma, then I would have PV to power gamma is constant, which is adiabatic. And then what's the difference between isothermal and adiabatic in terms of plot? Let me bring another color and show you. Look, guys, this curve, the blue one is isothermal process. With the adiabatic, it's not constant temperature, but it's moving from one temperature to another temperature. This is the isothermal. Adiabatic. That's why the adiabatic has more curvature than the isothermal itself. You can see there, adiabatic. So normally the adiabatic goes from the isothermal curve to another isothermal curve. So that's why with the adiabatic, it's more curvature than isothermal. And why more curvature? Because here PV to power 1 equal to constant. But here PV to power gamma is constant. And my gamma is greater than 1 normally. So that's why the curvature is more. The more is the power V, the more is the curvature. خلاص? And last thing here we want to say is isochoric process. With the isochoric, V to power infinity is 0. So I will get, P to power infinity means indication for the volume as constant. So that's why here I have constant volume, which is the vertical line. خلاص؟ إنزين دكتورة, if it is none of those, يعني it can be a delta between 0 and 1 here in this region, or it can be delta between 1 and any value that is less than gamma but greater than 1 here in this region. So that's why polytropic, which is PV to power delta is equal to constant, is applicable for any process, any path. And it's not only PV but also TV to power delta minus 1, TP to power delta minus 1 over delta equal to constant. And then, in case they give me such a question, what will they get? What they should give me in the question? They should either give me the value of delta, or they should give me at least two properties, yani T1 V1, T2 V2, and I can find delta. Okay? So this is how polytropic work while solving problems or while dealing with a problem. So once you define the delta, you can solve the problem. Indeed, for those who want to solve more problems from other textbook, many textbook, instead of using delta, they use N. Okay, so it's either called delta or it's called N in some other textbooks. خلاص? So with that, because it is similar to ideal gas, because it's similar to the adiabatic, the same equation that I derived for the adiabatic is here, but instead of having gamma, I have delta. For the Q, you can apply in the first of thermodynamic, replace W with this term, substitute and find the Q. But you don't have to know the derivation. If you are interested, you can you can send me an email and I can explain the derivation for you. But it's not given in your book, although it can be derived. Okay, guys. So with this, for the polytropic, we define Q, W, and of course delta U, delta H is the same. Integration CVDT and integration of CVDT for the delta H. خلاص? Okay. I think with that, we are ready to solve any problem. In summary, I explained 4 different paths plus the 5th path, which is the polytropic, that covers any path or any process. Any question before we leave? Now, we should solve example 3.3. But what I will do this afternoon, I will solve the problem and I will solve some tutorials of problems as well. Any question before we end the lecture? Hello? Any question? No? Okay, no, thank you. They said no, thank you. No, no. Okay, so things are clear. I hope it's clear. Clear?
Yes.
Can I leave? See you at 1 o'clock? All right, lecture, I think has been recorded. Okay, see you at 1 o'clock today afternoon. Bye-bye.